Good morning, everybody. Today, I wanted to go over the introductory material on electron configurations for you in class. So I just wanted to get you started with a simple lesson on electron configuration. So we're going to look at how electrons are arranged in an atom. Up until this point, we really haven't gotten very specific with the locations of electrons. You've done plenty of practice with identifying the number of electrons that an atom would have, given information from the periodic table. You also looked a little bit into ions, which we'll cover a little bit later in the week. So just as a reminder for you, the atomic number is always going to be equal to the number of protons that an element has, and that's unique to the element. And you also know that the number of electrons will also correspond to that number as long as you are talking about an atom, and atoms by definition are neutral. So the number of positive charges of the quantity of protons will offset the number of negative charges for the electrons. The number of neutrons, as a reminder, is found by subtracting the mass number, which is the sum of protons and neutrons, minus the atomic number, which is just the protons. Also, as a review, the protons and neutrons are located in the nucleus of the atom. And based on the wave mechanical model, we have defined that the electrons are located in the electron cloud. So if you think about the nucleus as this concentrated area of mass that's very small, where all the protons and neutrons are located, the electron cloud would be the three-dimensional space surrounding the nucleus where you're likely to find electrons. Now, within that electron cloud, we defined the term orbital as the region where there's a high probability of finding an electron within that cloud. So there are different regions of space surrounding the nucleus where you're likely to find electrons depending on how much energy they have. We're going to get pretty general right now, but we'll get really specific later in the week with the locations of electrons. So within the electron cloud, we have regions. So if you think about generic to specific, so think about the school building as being the electron cloud, and the students are all electrons. So within a school, we know we have lots of students. Within an electron cloud, we know we have lots of electrons. Now, also within our school, we have different floors to our building. Just like your classes are located on different levels or floors, electrons are located in different levels as well, and they are called principal energy levels, or PELs. Sometimes you'll also see them called shells or just energy levels, but there's lots of interchangeable terms here. The principal energy levels, PELs, give you a general idea of how far an electron is located from the nucleus of an atom. Atoms can have up to 7 PELs, depending on how many electrons an atom of a particular element has. The smaller the element, the fewer PELs it needs. The bigger the element, the more PELs it would need. And again, depending on their location, the number of the PEL that an electron is located in will correspond to a differing amount of energy that that electron would have. So if you are an electron that is in a low number PEL, the first PEL, for example, that's the one closest to the nucleus, you would not have a lot of energy. But if you are farther away from the nucleus, you would have a higher amount of energy. So it goes from low energy close to the nucleus to high energy far away. And here's just a diagram depicting that. So we know now that this idea of these orbits is not accurate, but it's easier to draw than just being vague and saying, oh, it's a region where I kind of can find something. So we're going to just draw these shells to make it easier to identify the locations. So if you're in the first PEL, you can see those electrons would be located closer to the nucleus. They would not have a lot of energy versus the second PEL, third PEL, and so on and so forth. You do need to memorize, actually you don't because on the periodic table, but you need to have a familiarity with the total number of electrons that could be held in a given PEL. So the first PEL, which is closest to the nucleus and therefore the smallest, can only hold up to 2 electrons, and then it's full. It cannot physically hold any more. If you have a second PEL, the second PEL can hold up to 8 electrons until it's maxed out. The third PEL can hold up to 18, the fourth can hold up to 32. Now there are other PELs 5 through 7, and they would hold increasing numbers of electrons, but for this course and the majority of the elements you'd be working with, you're really only dealing with the first 4 PELs. There is a mathematical equation, I guess it's an equation, that you can use to count the total number, and it's 2n squared, where n is the number of the PEL that you're in. So for example, if n is equal to 1, 1 squared is 1 times 2 is 2. If n is equal to 2, 2 squared is 4 times 2 is 8. N is equal to 3, 3 squared is 9, times 2 is 18, and then 4 squared would be 16 times 2 equals 32. So knowing that relationship, you could predict the total number of electrons in the fifth PEL. So 25 times 2 would be 50. But again, the first 4 are the ones you do need to know. The electron configuration is the term we use to describe the arrangement of the electrons within these PELs. All it does is tell you how many electrons are in each PEL for a particular element. You're always going to start close to the nucleus where the lower energy would be and work your way out. Once the first PEL fills up, if there's leftover electrons, they get dumped into the second PEL. If there's still more electrons left over, they get dumped into the third PEL, etc. Once you get into some larger elements, the PELs start to overlap a little bit, but I will explain that to you in class. The information for general basic electron configurations is on your periodic table. So it's given to you in the key on your periodic table, so have that handy. This is the key that is on your periodic table. And in the lower left-hand corner, it is labeled that is the electron configuration for a particular element. The way that you would read this is you would just say 2,4 or 2-4. The 2 means that there are 2 electrons. They're in the first position. So those 2 electrons are in the first PEL for carbon, as in this example. Here they are in the diagram. And now that first PEL is full because the first PEL can only hold up to 2 electrons. Well, carbon atoms, being neutral, would need a total of 6 electrons to offset their 6 protons. Well, we already used up 2, so we have 4 left over. Those other 4 electrons will get placed into the second PEL further from the nucleus. So that PEL is not full, but that's all the electrons that we need to complete the electron configuration for carbon, because carbon only needs to have 6 total electrons. And so these numbers will add up to that number. So here's a couple other examples. So for magnesium and zinc, look at your periodic table and be able to identify these 4 points. So for magnesium, you find that on the periodic table, it's to the left. Its atomic number is 12. That is given to you, that's bold-faced lower left-hand corner. So that means that a magnesium atom would have 12 protons in its nucleus, and since we're talking about atoms, it would also have 12 total electrons to offset all the positive charges. The electron configuration for magnesium is given to you right underneath the atomic number, and it's 2, 8, 2. This makes sense. 2 plus 8 plus 2 equals 12. That's the total of 12 electrons that we need. The number of electrons in each PEL should also make sense. I need a total of 12 electrons. The first PEL can only hold 2 electrons. It is full. So I've used up 2 out of the 12 and I have 10 left. Well, I can't fit 10 electrons into the second PEL. I can only fit 8. And now it's full. So now I've taken care of 10 out of the 12 electrons, and I have 2 remaining. They will get dumped into the third PEL. So now I have a completed electron configuration. It adds up to the total number of electrons that I need. Number of PELs occupied would be 3. There are 3 PELs that have electrons in it. Only the first 2 are full, but that doesn't matter. There's electrons located in 3 of them. The other example for zinc, So zinc has the atomic number of 30. It's towards the right on your periodic table. That means that zinc has 30 protons, and since it's an atom, it would also have 30 total electrons. The arrangement of those electrons is given to you right underneath zinc's atomic number, and it's 2, 8, 18, 2. So if you add all of those up, you get 30, which is what our total needs to be, and the sequence should make sense as well. I can only fit 2 electrons into the first PEL, and then it's full. I have 28 more. I can only fit 8 of those into the second PEL. Well, now I have 20 electrons left. I can only fit 18 of those into the third PEL. The remaining 2 will go into the fourth PEL. So there are 4 occupied PELs in a zinc atom. Magnesium and zinc, magnesium would have 2 for its number of valence electrons, and zinc would also have 2 for its number of valence electrons. It's just the last number in the configuration. There are certain electrons that are very special in terms of their characteristics, and they have their own term. They are called valence electrons. Valence electrons are the electrons located in the outermost PEL of a particular atom. So on your electron configuration, all that means is it's the last number in the configuration. The reason why these electrons are so important that they get their own designation is that these are the electrons involved in any sort of chemical bonding that an atom would undergo with another atom. The reason why these are the ones that would be involved is because they're the most accessible, they're farthest from the nucleus, and most likely to be able to interact with other atoms. These electrons give an element its chemical properties. So you can make a lot of predictions about the types of bonds that an atom can form, or the likelihood for its reactivity. Is it likely to lose the electrons or gain the electrons based on the number of valence electrons it has? And that's something you'll learn as we progress through the course. But this is very important. So if you have 2 elements that have the same valence electron number, you would be able to say that they have similar chemical properties. They're not identical because the elements themselves are not identical, but they would have similar properties in terms of their reactivities. The next blank here, this would be the last number of the electron configuration. So going back to our prior examples of valence electrons. Moving on a little bit from the total electron configurations is looking at what's called a Lewis dot structure. A Lewis dot structure just is a diagram that depicts just the valence electrons. Because the valence electrons are the ones that are most important in forming compounds and making different molecules, you're going to very frequently have to draw these symbols. And if you had to draw all of the electrons all the time, it would just be a huge pain in the butt. It would take too long. It would take up too much space. So scientists came up with this shorthand way of denoting just the valence electrons of an atom. And it's called a Lewis dot structure. Some dead guy named Lewis figured it out. And conveniently enough, we're going to put dots around the symbol. Now, when you make a Lewis dot structure, you will never have more than 8 dots around a symbol, because if you look at your periodic table, the number of valence electrons maxes out at 8. So what you would do, so for example, if you had magnesium, and we said that magnesium had 2 valence electrons, you would just show those 2 valence electrons as 2 dots. Basically, you want to kind of box in the symbol. You don't, if an element had, for example, 5 valence electrons, you don't want to put all 5 across the top. You kind of want to box it in with a maximum of 2 per side. There is a particular sequence to follow when you are doing your Lewis dot structures. I will explain this further to you in class, but if you have 1 valence electron, it would go at top left of the symbol. A second valence electron would go top right. Third valence electron, you're kind of working right clockwise, but then it gets weird. Your 4th valence electron would go here. Your 5th would go on the left-hand side, and then you would go back around 6, 7, 8. So again, it's kind of weird. You don't have to do it that way. You won't get marked wrong if you don't do it this way, but there is a reason for it that I'll explain in class. What I want you to do is make sure that you do 2 per side, or a maximum of 2 per side. So if you were doing the Lewis dot structure for aluminum, if you look at your periodic table, has 3 valence electrons. So I would do 1, 2, 3, because I put 2 on this side. I don't want to put any more on that same side, so I just kind of work my way around. Again, as long as you have the proper symbol and the proper number of dots, as far as Regents grading goes, they don't get too picky. So if you had to do the Lewis structures for these, for helium, you write down the symbol for helium, which is He. You look at its electron configuration, and it's only a 2, so that is the number of valence electrons it has. For sulfur, its symbol is S. You look at its total electron configuration is 286. The 6 is what we're going to work with. So 1, 2, 3, I'm going the proper order, 4, 5, 6. But again, you could do 2, 2, and 2, it's fine. Boron symbol is B. Its electron configuration is 2-3, 1, 2, 3. Nitrogen's configuration is 2-5, 1, 2, 3, 4, 5. And then neon's symbol is Ne. Its configuration is 2-8. So neon would max out with all 8 dots. When you are drawing these for grading purposes, you need to make sure your dots are large and in charge, so I can tell that you know what you're doing. If it's just like a faded little dot and we're not sure if it's supposed to be there or not, we are not giving the benefit of the doubt. So be careful with it. So that's an introduction to simple electron configurations using the periodic table, what valence electrons are, and how to draw a Lewis dot structure. So now you're prepared to complete some practice exercises on this topic.